So I'm going to talk to you about, well, the title is Cheap Solar. Actually, I'm going to give a sort of a brief discussion about where solar is at the moment, and then actually show you some technology advances we've been making here in Oxford about a new solar technology that could disrupt the current technology and create a step change in performance and potentially cost. So to sort of just understand the scale of the available source, I'll just bring up this map here that shows the map of the Earth. And these little black dots represent the area we'd require to produce all our electricity at 8% efficient solar cells. Bear in mind, current PV modules are around 15% efficiency. So it's actually even half this area if you're using current silicon modules. So that's not very much. If you compare it to something like farming, about half our land's actually used for farming. And this is sort of an example of the footprint of human activity on planet Earth. So it's a dramatic difference. It's not that we have to give up a load of farmland to produce PV power. It won't impact the environment very much at all. Actually, 60% of this farmland's cows or cattle. Now, that's not a different talk from me, but it's just an interesting observation that we could also just all go vegetarian and then save at least half our planet from farming, and probably a load of diseases as well, but that's someone else's talk probably. For the UK, it's not all that bad in the UK. It isn't very sunny. It's about less than a third of the amount of sunshine as in the Sahara Desert, but there's a lot of sunshine in the Sahara Desert, and there's a reasonable amount in the UK. The total land area per person in the UK is about 4,000 square meters. Square meters, yeah. Farmland is about 2,000, around 50% of this, and buildings is about 48, and roads is about 63 square meters. If we converted this all into PV, so used all our rooftops, all our roads as photovoltaics, we'd produce 58 and 76 gigawatts average electricity with the solar irradiance we have in the UK. So that's an average irradiance of 100 watts per square meter. So on a really bright day, you've got about a kilowatt per square meter. So this is genuinely the amount of PV energy. That's not the amount of installed PV. We'd have to install around half a terawatt of PV to get that amount of average irradiance. Just on the economics of it, again, as a back-of-the-envelope calculation, if we could get the PV down to around $1 per watt or £1 per watt, that would cost around £500 billion. So to bear in mind the cost of that, that sounds like quite a big number, but you can do this over 25 years, and it's possibly affordable. But if we can reduce that further, then it could become very affordable. So what's the current PV technology that you see on houses and in solar fields and farms? It's silicon. Now, this is a diagram. Probably doesn't mean very much to many of you. This slab here, if you like, represents a silicon wafer, and it's around 300 microns in thickness. So that's about sort of 10 hairs thickness or 5 to 10 hairs thickness. So it's quite thick. You can actually see this thing. It's like a very thin sheet of paper. And it absorbs light within the middle of this material, and that generates charge when it absorbs sunlight. And you notice this is P+. That means it's positively charged contact. This N here means it's negatively charged. And that's a way it's called doping of the semiconductor. And what that assures is that the current flows in one direction. So that's how a solar cell works, very briefly. I'm not going to try and explain it in any more detail. But silicon only works when it's very, very pure. If there's any defects in there or any impurities, the charge doesn't get out. So the reason why silicon PV has been historically expensive is that it's been a very energy-intensive, cumbersome process of making these really pure materials and then putting on all these contact layers very carefully and stopping any defects or impurities at the interfaces. Despite that, it's done pretty well and is doing pretty well. This is about a 600 megawatt solar farm in India, one of the largest in the world. And the sort of installed or solar global photovoltaic capacity that is predominantly silicon PV has doubled about every 2.45 years. I think you got some more up-to-date figures on this earlier, this sort of trend. But clearly it's set, in fact, by 2030 or before, we should just about be able to deliver all the electricity demand by PV if this continues in a nice straight line. But, of course, it's got to increase by at least 100-fold to do that in actual quanta. So how do we achieve that? And the other question is, how has it been achieved so far? Well, that's quite simple by looking at the historic cost of silicon PV. In 1977, it was something like $76 dollars per watt peak, and that's dropped down to about 74 cents per watt peak. So a 100-fold reduction over this time period, and this isn't set to plateau yet. There's two things that are happening. The silicon cells are being made more cheaply. The silicon's getting even cheaper, although it's getting very inexpensive now. And the efficiency's going up. The current least expensive PV technologies are based on microcrystalline silicon. It's the Chinese silicon, and the modules are around 15 to 16% efficiency. There's a whole new generation of PV coming out primarily from the companies in the USA that's going to deliver 20% efficient silicon modules, and that's going to get down to this similar sort of price. So this is still set to grow, so silicon PV's doing well, and in some places in the world it's already generating power at around $26 per kilowatt hour, compared to coal at about $0.1 per kilowatt hour. So it's not far off. If we could reduce the price by twofold or threefold, it would really start to produce power much less expensively than coal. So is there a cheaper way? So now this is where I'm going to start to veer more towards some science and stuff related to what we're doing here. Is there a cheaper way of making silicon? Well, this paper here that I'm showing you was published in 1985. So bear in mind the cost of silicon PV in 1985 was still well over $10 per watt peak, and it looked much more expensive than oil. So people are experimenting with dyes and organic molecules. These things are sort of a few dollars per kilogram, so it's very inexpensive materials. If you can make a solar cell as efficient as silicon from organic dyes like this, then that could be very, very good. The first cells reported were around 1% efficiency, so they had some way to go. But over about the last 10 to 20 years, there's been a lot of research effort on organic photovoltaics, mainly driving what we're calling bulk heterojunction approaches. I'm not going to go into the details, but instead of having a solid layer of organic absorber, there's two materials, the P and N type material, all mixed together. This enables charge to move out of the P-type material, out of the positively charged material, into the negatively charged material, and get out of the device. If you try to make a solid layer of an organic absorber, all the charge doesn't get out. The charge can't transport that far. They actually form what's called a tightly bound exciton, for anyone who's interested in the more details. So we have to have this bulk heterojunction, which is either made of all organic materials, or it's a hybrid approach where we're using metal oxide nanoparticles here coated in a dye. And this is called a dye-sensitized solar cell. These technologies have pushed up the power conversion efficiency to around 12%, but they look like it's going to be a big challenge to get them much further. And silicon's still coming down in price, so we sort of need something else, another sort of material that's cheap and can make solar cells more similar to silicon or crystalline materials. So as a family, again, hybrid seems to be the word of the moment, but it simply means a mixture. In this case, a mixture of organic and inorganic. It's not a combination of electricity and petrol, but it could displace that, hopefully. Well, displace the petrol part anyway. Anyway, this is, again, a paper, just to give you an idea on the timing of this, from 1995, investigating organic, inorganic metal halide perovskites. Perovskite is a type of crystal structure, and all these dots and bars represent bonds and atoms. That's basically a crystalline material. These materials are processed very easily from just mixing two salts together, and they dry and they crystallize into a thin semiconductor film. But they weren't investigated for solar cells till quite recently. In 2009, a colleague in Japan reported the first dye-sensitized solar cells. Again, this is one of this bulk heterojunction, distributed junction, using perovskites as an absorber to replace an organic dye. We started working on this technology in collaboration with this Japanese colleague, and what we discovered was we didn't need this separate TiO2 that was an N-type, the negatively charged semiconductor. We could get rid of it and just use an insulating scaffold. Again, I won't go into the details. I'm trying not to lose you all here, but the efficiency improved. What we got was a big jump up in voltage. and the voltage actually became much higher than the voltage you get for crystalline silicon, or indeed you would get for crystalline silicon if it was the same band gap absorbed in the same region. So it suddenly looked like it's a competitive technology. Of course, as well as voltage, we need to get current and fill factor. I'm realizing probably most of you don't even know what this diagram is here. This is a current voltage curve. On the left-hand side, we've got photocurrent and applied voltage. But we measure the efficiency as obviously current times voltage, or the power output, and that's the important parameter. So since then, we've discovered that we don't even need the insulating porous support. We can just make a thin film by a simple vapor deposition or solution processing, and these devices are now 15% efficiency, and our best devices are a little over 17% efficiency. So we've suddenly had a big step up, and if we look at the trajectory of this, here these are the perovskite cells in terms of efficiency. This is crystalline silicon here with the best lab efficiency at 25%. So potentially within a year's time, of course this is definitely artistic license rather than but I like trends at the moment. Of course, at some point all these technologies have a little turn the corner, hopefully not yet, and by 2016 we might be competing with gallium arsenide, which isn't very long. At that point, I should point out that these materials are extremely inexpensive. Again, in principle, 10 pounds a kilogram at scale that can be processed low temperature without any real thermal input, nothing more than drying and about 100 degrees treatment. So in principle, it could be practically free active layer. There's more to a solar cell. It has to be in glass. There's electrodes, etc., etc. But it could be very, very inexpensive. So I'm just going to talk about one application, well, a few applications, but firstly one that we think would be suitable for this technology and a deployment for PV is buildings. There's not buildings. We've got all this support, all this structure, if you like, and the power demand there. If we can coat that in PV, then we can use it on site and should be able to drive down the price of PV because everything's there, the wires are there, the demand's there. The problem is our semiconductor's brown, so we could probably sell it in a few places, but not many. So what can we do? What we discovered was we can actually make these films with the semiconductor form little islands, and then they're semi-transparent. The light passes through the gaps between the islands, and the little islands act as little solar cells. And we control the transparency from 80% down to practically zero, and the solar cells actually work. So what we get is a semi-transparent, neutral-coloured photovoltaic device. Now I'm trying not to turn this into a pitch. I'll probably get told off, but we have a spin-out company, Oxford Photovoltaics. It's based up at Begbrook Science Park, and we're scaling up this technology to produce stable and efficient modules for deployment in a number of sectors. And I'll just quickly tell you where we think this stuff's really going to meet a good demand. One is building integrated photovoltaics. The other is utility PV. Of course, when we match the efficiency of silicon, it could in principle drive down a lower cost PV, and that's what we're really interested in. As well as that, we can make a wider band gap. So we can absorb the visible region of the spectrum in these solar cells and generate a higher voltage and stick that on top of silicon. It's called a tandem solar cell. And that could step up the efficiency. So as well as not inducing very much extra cost, we could end up delivering, in principle, 30% modules, which would be a big improvement. Now, of course, I'm being entirely biased and optimistic here, but we'll see where we get. And the final one that I quite like, that I think could be very interesting, is solar greenhouses. This is taken from a company, Seawater Greenhouses, where they make greenhouses for arid environments. They use salt water to pump it over big filters to get evaporative cooling. So it's actually for getting about a 20-degree lower temperature inside than on the outside. Now, if we can combine that structure with PV as well, we can produce water, food, and power in arid places that were otherwise desolate. So that could really solve quite a few problems. And in terms of the work, I'd like to just acknowledge my research group and funding. And thank you for your time.